All right, so last time we did differential equations, right? And I have coffee too. That should help. Okay, so we said we were going to look at a application. So does anybody know about Torricelli's law? So we did a actually. Here, let me open it up. The problem. Okay, so in the files that I gave you last time, I think it was the very first problem. Yeah, this one. So we have the a cylindrical tank, has a height of 9 feet, radius 2 feet, filled with water. Water drains through a square hole, size 1 inch at the bottom. Determine the water level at times t. So this is the differential equation. So we're going to derive that in a minute, and then we'll work out the problem. So we understand the idea, right? So what Torricelli's law says is that the velocity of water exiting the hole is proportional to the height of the water inside of the tank. So specifically, the velocity of the water is equal to -2 square root of the gravity times y, where y represents the height.
Velocity of the stream at what point?
At the bottom of the hole. Yeah. So you have a hole. So let me draw a picture. So we have, let's say, some kind of a doodad here. And so let's put a little hole down here. And so let's say we've got a little tube of water. So this is filled with water here. Okay, so what we want to do is we want to write down a differential equation that expresses the this problem. So so I'm going to give you the strategy, and you'll help me figure out what the differential equation should be. So the strategy is to take a snapshot in time, and so take a snapshot. Snapshot of time delta t. I don't have a camera. I wanted to actually bring one to demo, but I thought maybe I figured it was probably a little bit much. But I was gonna get a little bottle and put a hole in it, and maybe you guys can do it. Maybe it could be a fun little project for you guys. For fun, if you want to. You guys can do it. Okay. And so we're going to take a snapshot in time of the water going down this hole. So let's label a couple of things first. So let's say this, so in this, let me see. All right. So obviously there is some dependence on the size of the hole, right? Yeah. Okay. So let's call that something. So let's say that this is let's call this base of the hole. Let's call that B. Okay. Now, so if you take a snapshot in time, you have a certain amount of water that exits the tank, right, and goes into the hole. So let's assume that in that snapshot in time, this amount of water. So the amount of water that exits in that snapshot, that delta t in time, is the water that's inside of this little tube here, let's say. So this what I just drew represents the amount of water exiting the tank in delta t seconds. Okay, so let's label this H. So if I were to ask you how much water exited, you would say it would be the volume of, this little tube doodad, right? Which would be just simply equal to B times H, right? The base and then times the height, right? Based on the way that I labeled it, right? B times H. Okay, now in that same amount of time, some of the water exits the tank, right? So let's label that. So some amount of water that will be approximated by something like this. And so we lost this much height. What should I call it?
Change of y.
Delta y, right? Because that's the change in the height of the water. And then now what do you notice about so you want to relate the volume of the water that exited, is exiting out here, plus, or not plus, but you want to compare it with the volume of water that is leaving the tank, right? So, but what do you notice about the water leaving the tank? Or if you wanted to find the volume of water leaving the tank, how would you find it? The same idea, right? It's a cylinder, but
Could you take the volume of that code and differentiate, kind of like the maximum?
well, we want to approximate it with a cylinder, right? Because that keeps things simple, right? And then we'll, so delta y will get infinitely thin and all that. But what do you notice specifically? So, like, if I'm going to write down the volume of this cylinder that I just drew right here, how would I write that? Okay, so the volume, so volume in tank is equal to, volume in tank, let's write this, change in volume in tank for delta t seconds, or whatever the units are. So the change in volume would be delta y times the right, in this case it's pi r squared, but in a general case it would simply be the no, because remember, so you're trying to come up with a formula in general, right? So like if, for example, if I have a tank that's looks like that, would it be the same formula? No, right? It's not the same formula. So it's dependent on what the shape of the tank is. But in general, this would be simply the area of the the area of the cross section, right?
Okay, yeah.
But what do you notice about the area of the cross section? Is it always the same? Changing. Okay. So we're going to call that A of y. So this represents, so this A of y, this is the area of the cross section, and it's a function of y because typically it changes as you go down, right? Does that make sense? Okay. So so we know that those two quantities of water are identical, right? The amount of water that exited the tank and the change in the amount of water inside of the tank, those are the same, right? So we set those equal to each other. So, why don't I let's do this before we set them equal to each other. Volume outside the tank. You guys already told me what it was, right? This is B times H. That's the other one that I told you earlier, right? Okay, so we'd set those two equal to each other. So I have that the amount of the change in the volume of water inside of the tank is equal to the change in the volume of water outside the tank. But now we have a bit of a problem because B we can find because it has a certain physical dimension, right? It's either circle, square, whatever it is. But so you should be able to find that as long as you have its measurements. But H here, how do you find the height of the water?
Oh,
I have a quick question. That red cylinder at the very bottom, is that something does that represent only water, or is that part of that tunnel?
Yeah, no, it's water. So this water right here, not a good color there. Okay, all this water right here represents that water right there. So you take a snapshot of time delta t. The water exits this top and corresponds to the same amount of water on the bottom.
Same volume.
Yeah, so that's why you're setting them equal to each other, because it's the same amount of water. Okay, but we still have a problem with this H, because how can I find what H is?
where's Y though? Where's the X?
Y
We need
minus
to put the X.
No, we don't need the axis. It's related to something
Do we
that
know the diameter or the radius of that small hole at the bottom?
you do know. It's assumed that you know what it is,
So
right?
in theory, the water's going to get to that point where it's that radius, right?
Yes.
And then you know that height.
Yes, but how can you find the height? Okay, let me put it. Oh, yes.
Are you trying to relate it to time?
Well, yes, we're talking about a snapshot of time delta t.
So it would just be from time 0 down to whatever time you stopped, right?
Ye-
So
Yeah, we
You
don't
just
know
have
the flow rate. We don't know the volume of the water actually exiting. That's the problem. So we can't just find H.
But you do know something. There's something else that we haven't used. It's up on the board. Or the screen. Yeah, Torricelli's law, right? What does Torricelli's law tell you? Tells you how fast it's going down, right? So if you know how fast the water is going down, so this right here tells you how fast the water is going down, right? So at this point, it's simply a matter of
Take the derivative.
distance is equal to rate times time, right? So what we're looking at is that this distance, the distance the water traveled, right, is equal to the rate at which it travels, which is that velocity, right, times the time, which is how much time? Delta t, right? That's how much time. That's our snapshot in time. So H here, H is equal to the rate, which is negative 2 square root of g y, and times time, which is delta t. So there we've got our. So if we plug that in, we would get a of y, delta y, is equal to the base of the hole, right? The area of the hole. I'll put the 2 better in front. So I have negative 2 square root negative 2b square root g y delta t. So if I'm going to write this as a differential equation, then what would it look like? dy over dt is all that stuff, right? Negative 2 b square root of gy all over a of y. That's it. So if we're doing, well, do you guys have any questions? Does that make sense?
Delta y is dy.
Yeah, so that was, so this is the change in y, and then you let delta t go to 0, and so then they're differentials. So, okay, so why don't we do that, the problem that we just had a second ago here. So we have cylindrical tank. This is actually kind of an easy one, but that's okay. So, hey, hello. Okay.
I'm sorry, was there a dt at the end of the...
No, we moved it over to the left. So we have a tank, height is 9 feet, a cylindrical tank, height is 9 feet, radius 2 feet, filled with water, and the square hole is 1 inch at the bottom. And so we'll verify this formula that we have right there. So let's draw a picture. So this is our example. So it's a cylindrical tank, square hole at the bottom. So the height of this was 9 feet. Square hole, 9 feet, or 1 inch, 9 feet. Okay, so we derived all our stuff. So why don't we figure out what all this stuff is? So what is B equal to?
1. Oh,
Wait, let me just make sure.
it's 1 square.
What do we have to be careful with?
Units.
Yeah, units, right?
Feet,
Yeah. So we've got feet for the height, inches for the hole, right? So we should turn that into the inches into feet, right?
so 1/12 foot.
Okay. So this is so the base is 1/12 of a foot squared, right? You guys agree? And then what is G?
32 feet per second.
Okay. 32 feet per second squared. Well, I don't know. Should we put the units in? And then what else? So y. What about A of y? So what do you notice about the area of the cross section?
It's consistent.
Yeah, it's always going to be the same, right? So what's the so first we have to, what do we need to be able to write down the area in terms of y? What do we have y as? Y representing the height of the water, right? So where should my axis be? Yeah, at the bottom. So my axis should be at the bottom. And so y is going to be pointing positive up. So
Yeah, we can barely see the. Yeah.
I can see it.
I didn't realize you wrote
It's like
something.
or something.
He's just pointing.
So yeah, I didn't want it to be too dark because it's, the axis. So, but anyway, so you take an arbitrary slice, and so the area of that slice, what is it equal to?
Was the radius 2 or is that diameter? So
Yeah.
8 pi?
Yeah, the radius was 2, and notice that the radius is constant, right? So because it's a cylinder, the radius is constant, but it's not always constant. So if it's not, then you find it the way we've always found all these other things. So the area is pi times the radius squared, right? So that would be how many pi's? 4 pi's. All right, so plug it all in. Plug it all in. So we get dy over dt is equal to, what do we have here? So this is, well, negative 2 over square root 32y. I'll put the 12 squared on the bottom, and then times 4 pi. So what is that? If we simplify a little bit. So 144, so if we divide by 2, that would be
72.
okay, so 72, and then, well, let's take a, what can you take out of there?
So it'll be bringing a 4 to the outside, so it'll be negative 8.
4, and you'll have a root 2 inside, right? So, okay, so then we'll have, so this 4 will cancel with this 4, right? So this 4, adios amigo. Here we're left with 72, right? And then we're left with a
Root 2 over root 2y on top.
root 2y over 72 pi. Okay. So what does that say right there? If you were to interpret that differential equation, what does that tell you? If you were to read it in English. The rate of change of the height of the water is
That.
proportional to, so you've got this constant, right? But it's proportional to the square root of the height, right? Square root of the water level at that particular point in time.
If you
Yeah.
let the units in with the, it would be just y would be meters on top or feet, and then it would be time on the bottom. When you direct, meaning to that, like the time would be on the bottom of that.
Well, yeah, it is. Yeah, so this would have to be meters per. Well, no, in this case, feet per second, right? Yeah, we just took them out because it's math class.
So every 72 pi seconds, it would be, or whatever time, it would be negative square root 2y.
Well, no, this is telling you the rate of change of the water level. So this we can. Well, why don't we solve this? How do we solve this? This is called what kind of a differential equation? It's a separable differential equation, right? Well, and why don't we add the initial condition? What's the initial condition? Y of 0 is equal to
9 feet.
9 feet, right? That's the height and the initial time because it said that it was full. So, all right, so this is a separable differential equation. How do I solve it? What's the first thing I do? Let's solve it over here. Okay, so divide by negative square root of 2y. Sure, we can do that. Is equal to 1 over 72 pi dt. And then what do we do?
Integrate both sides.
Integrate both sides. So then on the left, what do I have? So what do I do first with that negative root 2 business?
Bring it out.
Just bring it out, right? So I'll bring out the negative 1 over root 2. And then the antiderivative of the left side is natural log of y is equal to,
Is this y under square root 2?
Sec out.
Or no?
oh shoot, yes. Sorry, thank you. Yes, yes, yes. The y is under the root, right?
Yeah, that's right.
Okay, so what is it?
Square root of 2 over 2? No, 2 square root of 2.
Yeah, so you bring it up, right? So it's y to the negative 1/2, so you add 1, which gives you
Y to the 1/2.
y to the 1/2, right? Okay, and then,
Times 2.
yeah, divided by 1/2 or multiplied by 2, right? So it's negative 2 over root 2 y to the 1/2 is equal to 1 over 72 pi t. So then, yeah, don't forget your plus c. And then, what is it?
On both sides. 'Cause of that.
Yeah, but it doesn't matter because there's a constant on the left side, constant on the right side, but then you just put them together. You know? Okay, now actually, well, it's probably easier. Well, I don't know. All right, so let's solve for y. So what is it equal to? So we move the root 2 and the 2 over, right? So what do I have? So negative root 2 over 144 t. Well, we have to call it something else, right? Well, because you multiply it by those constants too, so let's just call it some other constant d. Okay, and then at this point we can find d, right? Because we have an initial condition, so that means how do we find d? We just plug it in, right? So we plug in our t value when t is equal to 0, y is equal to 9, right? So we'll plug it in, and we can find what d is, right? All right, so let's do that. So, so if I plug in 9 for y, 0 for t, I get that d is equal to 3, right?
Yeah.
Okay. So then I'm pretty much done, right? Because then y is equal to negative root 2 over 144 pi t plus 3, and then the last thing I need to do is get rid of that 1/2, right? Which I just square the whole thing. And that's it. So what does that represent? The height
at any given time.
Yeah. So this tells me the water level at time t, right? The water level of the tank, assuming what? What am I assuming in this case?
Flow rate.
Well, no, besides all the laws and everything. But this is a particular solution, right? It's a particular solution because I'm assuming that.
Oh, at time 0, the height of the water.
Right.
Is,
So I started off with water level of 9 feet, so a full tank. So if I plug in any value for t, then this should give me the water level at that particular point in time. And so if you if we go back to our doodad here. So that was the general solution, but that's pretty much what we got, right? Except the constant's different.
Y at t.
Root 2 over. Oh, wait. Oh, that doesn't look the same.
No, there's a root 2 in there.
I might have written it down wrong though. I don't think we did anything wrong.
It's starting.
It's what?
It's starting.
It's starting. What's starting?
Messes.
Oh yeah, but no, I don't think so. I don't think I messed it up. Well, we'll see.
That's it. So one of those is not right.
What is this? No,
I would bet this one is wrong. That's my bet. Well, because we didn't do anything wrong. Right? I don't think. Oh well. No. If it's off by a root 2. We can fix it later. If it's wrong. Which I don't think it is. What is it? Yeah. Start downing myself. All right. Okay. So does that make sense? Yeah. All that stuff. Okay. So questions.
Isn't it where's the area go? The area of the one you just did?
The area of what?
The cylinder.
Which
The
one?
you just did the last problem, the next problem.
The one without a angle. 4 pi? 4 pi, how do we get to 4 pi?
Yeah, area equals 4 pi. So there.
Oh, the area of the circle. So the radius is 2. So it's just pi r squared.
Yeah, I missed that.
Pi, I'm thinking 2 pi.
Are all of the shapes that we're going to be dealing with going to be uniform? Like,
No. I mean, it could be like a cone, but then at that point, it's the same as all the other ones that we've done. Like, so you just write a formula for the area, kind of like in the force.
okay.
So the idea is the same idea.
You just need to find the Jefferson equation.
Mhm.
Pi r squared, since R was
Yeah, using some type of similar triangles.
yeah, it's the AY.
What is it? That's gravity. So, yeah, so it's 32 feet per second squared. Okay. All right, so let's take a look at another application. Let's take a look at so let's take a look at models involving dy over dt equals to k times y minus I think, well, I forget if your book does k or minus k. It doesn't really matter. But what does this differential equation tell you?
It's like a string equation.
No. So if we read, what is that? This says that the rate of change
Times some constant k.
is proportional to.
Yeah, times some constant k.
Well, no. So k is just a constant of whatever, right? So whatever the situation is, but it's saying that the rate of change is proportional to the.
Current value minus
The difference between the value and the starting value. Does that sound like a situation that we've mentioned before, where the rate of change is dependent on the difference? No? It's the coffee cup, right? Yeah, the rate of change, so the temperature of the coffee cup, right? So if you imagine a room, right, at a certain temperature, and the coffee cup is super hot, right? You play it super hot, so the rate of change of the temperature, the rate at which the temperature goes to the room temperature is initially fast, right? And then as you get closer and closer to the temperature, then it starts slowing down, right? Does that make sense? So it depends on the difference. So if the difference in the temperatures is high, then it moves to that temperature, equilibrium temperature quicker.
Ever heard that hot water freezes faster than cold water? That has nothing to do with like this kind of.
Wait,
Hot
water
does
does
freeze
what?
faster.
Ever heard that? It's like a different like it does.
what's
Yeah,
to do with
that's,
that changes the enthalpy?
That was science
What did you give
showed.
Mr. Wizard going on?
Not science.
I don't know what you guys are talking about.
No,
But-
hot water freezes faster than cold water.
Yeah.
No, we did chemistry last semester.
How's that even logical?
We didn't have any equation like this to express it.
No, we didn't need to. It's a kinetic energy function.
I don't know. This sounds like shady business.
Seriously,
I'll go through like,
Um,
or even better, let's just go through the Jeremy upstairs. Talk to Jeremy upstairs in the lab. he's working right now.
So like.
He had a lot of cooling too.
All right, so let's write this down. Let's put it in terms of, so let's put T. So it's basically this same model. We have K and then T minus T naught. Here, be a little bit careful. This T naught, this is the ambient temperature. And this right here is the cooling constant. Now, what do you notice about so, you know, the same law applies whether you put something hot in a cold room or something cold in a warm room. So if you put the hot in a cold room, the temperature will go down, right? Decrease, right? So if you put something cold in a warm room, the temperature will increase. So where would you see that in the model?
It's reverse.
Just swap your initial and for the temperatures.
Yeah. So you would see that in the change in the temperatures, right? Okay. And then this cooling constant, what does that depend on?
The liquid.
Yeah, whatever the substance is that you're talking about, right? So it's dependent on the situation. So, all right. So let's do just a quick example of this. Why don't we do the one that we had earlier? Let's bring it up here. So we place a 98-degree cup of coffee inside a 30-degree room, assuming the cooling constant is 0.1 minutes to the -1. Well, I gave you the equation, but that's cheating. So let's see here. All right. So we have that information, right? So the rate of change is equal to the cooling constant, which was, what was it?
0.1 per minute, negative 0.1, or yeah,
Negative-
per minute,
Negative 0.1?
not just 0.1. Just gonna go one way or the other.
Well, the problem is that this is kind of annoying, but well, don't worry. There's a conflict between the Newton's law of cooling and the general model, and so when you in your book when they write down the Newton's law of cooling, I think there's a negative sign in front of the K. So, but I mean, it doesn't really matter. So I guess let's just stay consistent. So let's put the negative there. Okay, and then what do I put in place of the T?
The temperature, its initial.
Oh, maybe ambient temperature.
No, T of T, that's where we're going to.
You put T, right? You leave it as T because that's what we're finding. All right. Okay, so then minus
30 degrees.
30 degrees. Okay, and then we won't go through solving this, but how would you solve that? It's a separable differential equation, right? So just like the ones that we've been doing. And if we take a look at the, so let's take a look at the slope field again now that we've taken a look at the model. So here we can see, right? So we've got our coffee cup, which we don't really have it there, right? But it's 98. It starts at 98, so our picture starts at 60. Maybe we should bring up one. Let's see here. All right, let's bring out our old friend, Maxima. Okay. All right, you guys remember? Load. Plot df. Plot df. No, yeah, I put df plot the first time and that was wrong. Okay, so plot df. What was it? Y. Oh, leave me alone. Negative 0.1 times. When you put it in maximum, we have to put it in terms of y's and x's. So we can't put t, we have to put y. Y minus 30. And then let's give it x value. So if I'm going to let x go from 0 to, how long do you guys think it'll take the coffee cup to cool to 30 degrees?
21 degrees
10
in a minute.
minutes.
It's gonna say
10 minutes, all right.
30, 45.
Which is,
Thirty
wouldn't you, is it in seconds?
degrees.
No, it's in, what are the units? Excellent question there.
Celsius.
No, the time, but the time does it in seconds?
Minutes.
Per minute?
So yeah, the cooling constant is in minutes.
Okay.
Yeah.
680 minutes.
0 to 98, so let's go to 100. Oh, I forgot the comma here. And here. Okay. So you guys can do this right at home. Completely free program, and as long as you don't get any errors like I often do, it should work out. There we go. Okay, so, oh no. Replot. Oh, shoot. All right, well, whatever. Okay, so 98 right there. So the temperature, so 30 is about right here, right? So that wasn't enough time, right?
It's more like an hour and a half.
Uh-huh.
Okay, so let's do, how about
Few hours.
how about 60 minutes?
Because it's getting really hot.
Okay, so 60 minutes. Let's take a look. So you can actually find exactly how long it would take, right? I would hope you guys would be able to do that, right? You would simply solve the differential equation and find the time that it takes to get to 30, right? So here, let's plot it again. So 98. Kapow! There we go. So decreases. So the rate of change, notice the rate of change of the temperature is a lot faster in the beginning, and then it starts leveling off. And so, in 30 minutes it's almost there, but then the very last little bit it takes a little while to get to 30. And according to this model, it never actually reaches 30, but it does. But and so just a couple of things to add on here, since we've got a little.
It goes to infinity with that model. It never reaches 30.
Well, with the model, technically no, because technically no, but it, in real life it does. Right here, so this is called the equilibrium point, right? And that makes sense, right? Equilibrium point. So, and this solution right here, this one that I drew, semi-drew, this is called a steady state solution. The reason why it's called a steady state solution is because you start at, so like this is as if your coffee cup would have entered the room at 30 degrees, well, what is it going to do? Well, it's going to stay 30 degrees, right? So it'll just stay there. It's also commonly referred to as a fixed point, equilibrium point, fixed point, and then might as well introduce it now. Let's go back to our other picture here, which was our, let's do this one. Let's just take a look. Just one more term here. So right here, this is our model of, I think it was logistic growth. So we're going to look at this later again too, but this was the forest. So right here, how many equilibrium points do you see? Two, right? Where's one?
0.
One's at 0, so one equilibrium point at 0, right? And one equilibrium point at 1,000. Okay. But what do you notice the differences between the two?
One is converging to, the other is diverging from.
Exactly. Notice that this equilibrium point of 1,000, the solutions are going towards that solution of 1,000. So that's called a stable equilibrium point, or an attractor. It attracts. And then this equilibrium point, notice that if you start anywhere near 0, so if you start, well, it looks like 0, I don't know. It probably is 0, but if you start anywhere near 0, where do the solutions go? They go away from 0, right? So even if you start super, super close to 0, is it ever going to go towards 0? No. So it's always going to go away from 0. So that's called, so no matter if you start on the up here or down here, so that's called a unstable equilibrium point, or a so if you don't attract, what would you do?
Repulsive.
You are repulsive, yes. It's called a repeller.
Thank you. Really?
Not you, Ted, but you know. But it's called a repeller.
Untitled rolls and other chapters.
Okay, good times, huh? Good times. All right, so the next topic is quite exciting, because a lot of just like in integration, you have to in the real world, you don't always get nice problems that are solvable, using any of the techniques. So in math, I don't even remember the number, but there's a whole entire class on differential equations where you learn all the techniques. But even then, most real-world problems cannot be solved by techniques. So you must resort to
Computers.
yes, the power of computers. So
do it back in the early days.
Slide rule.
They didn't.
yeah, by hand making tables. They did. They spent hours making. Yeah. So you actually already know. We've already seen the graphical methods. It's the slope field. Now, I'm not going to really go over how to plot these, because if you really, really, really wanted to, you could plot these, right? Because, well, actually, let's do this. What do those lines represent? Mm-mm. Yeah, the slopes of, so the slopes at all the possible points on the plot, right? So let me I want to do, did I already plot df? Okay, I had an example here that I wanted to do. What was it? Y? Okay. So it's a really simple example. Sorry. Okay. So this is the differential equation. So dy over dx is equal to y plus x. So if you were going to plot this by hand, which I would not recommend, what you would really do is, instead of trying to kind of plug in points and figure out what the slopes are at those points, that would be a terrible way to go about it. A smarter way would be, even though it's a smarter way, I still wouldn't recommend it. But what you would do is you would say, for example, I want to know where all the points where the slope. So this is the example, right? dy over dx is y plus x. So I want to find all the points where the slope is equal to 0, for example. So then you go, okay, well, they're equal to 0 when y plus x equals to 0, right? Or in other words, when y is equal to negative x. So what is y equals to negative x? That's equal to a line, right? Going down. So if I go back to my, so all the points on that line, y equals negative x, would have a slope of a slope of 0, right? So see, if you follow along right here, see how all of these along the line y equals negative x have a slope of a horizontal slope, the slope of 0, right? Right? Okay. So then, and then you would say, okay, well, what about when you want to do, and again, I would not recommend this, but let's say you do, okay, I want to know where all the slopes are equal to negative 1, right? So then you go, okay, well then that's equal to when, so the slope is equal to negative 1 when y plus x is equal to negative 1, or when y is equal to negative x minus 1. So this line, negative x minus 1, is line going down, moved down by 1. And if you take a look right here, so right here along this line, the slopes are always negative 1. So along all the points y equals x minus 1, the slopes are slopes of those lines are -1. So those are called the isoclines. Isoclines, ISOCLINES.
Each hatch mark or that specific?
No, those like the points where the slope is equal to a particular value. Yeah. So anyway, so that's how you would. That would be the most efficient way to do it. Okay. But well, really, the most efficient way is to download Maxima and put it in. But but you get the point. Okay, now so those are the graphical methods, and then of course you can you can learn a lot of things from this. You can kind of play around, and Maxima is pretty cool in that it lets you kind of put in fun points here and do all kinds of fun stuff. What are all those called again? Solution curves, or also integral curves. They're also called. So each one of those red lines corresponds to a particular solution, right? Particular solution depending on what the initial conditions are, right? Okay. All right, good times. Now, so that's all nice and dandy. Now, what about numerical methods? So that's what we're really gonna focus on, and we're gonna start off with the simplest method of all. The simplest method of all is called Yep, that not Euler's method. Okay, and actually Euler's method is actually really, really simple. So what Euler's method says is that, okay, so you take a differential equation. Oh, sorry. In the form let's write it dy over dt is equal to some function of t and y. So for us, for the example that we're going to do, I'll write it down over here so that you can kind of compare. Is actually the one that we just drew, just in terms of t instead. So dy over dt is equal to y plus t. So the right-hand side, that's what we call capital F of t and y. So it's a function of t and y. Now notice, though, that t represents time, but what is y? Y is a y is the
Position.
function. Y is a function of time. Right? Because I'm getting the derivative of y with respect to t. So I write y plus t, but here y is actually a function of t. And so just to make sure that you're not incredibly confused already, these red lines, those represent y, right? So those are functions of t. So this is actually the slope field for that differential equation, right? When I put it in as y plus x because Maxima requires that you put it in terms of y and x. So, but it's really, I'm doing it in terms of t because we're talking about time. So, does that make sense? Okay, so, and actually the idea is very simple. What does this right here on the right-hand side tell me about my function? Tells me it tells me the rate of change, right? So if I know the time that it is, and I know where I'm at, then I can find the exact rate of change at that point, right? So if I tell you, okay, well, I'm at t equals to 2 and y equals to 3, the rate of change is 5, right? 5, yeah. 3 plus 2 is 5. So for this particular example, right? Right? Okay, so all right. So 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 check this out. All right, so this is the idea. The idea is very, very, very simple. Okay. We start at a point. Let's call it T naught. So whatever point, it really doesn't matter. I'm going to draw a little picture. Okay. Okay, so let's say at T naught, I am at Y naught, right? Right there. What is it?
Why not?
Why not? Sure. Why not? Where else would I want to be? Okay, now if I have my differential equation, and which tells me the rate of change, or also, what's another interpretation? Rate of change, derivative, slope of the tangent line, right? Okay, so let's say right here at this point, so I plug it in, right? Plug in T naught, Y naught in f of t and y. If I plug that in, it'll give me the rate of change at that point, or in other words, the slope, right? So let's say, bam, right there. That's the slope of the tangent. That's all I have. All I have is a point and the slope of the tangent line at that point. Then what can you do from that? You can approximate where you're going to be, right? Because you know the rate of change. So if the slope of my tangent line looks like that green line, wouldn't it be safe to say that if I decide that I'm going to take a step of a certain length, wouldn't it be safe to say that that would be my approximated value, that pink dot right there? So if this is, I'm going to call this, so this is going to be t sub 1. So this we're going to call h. This is going to be called the step size. So what is that y value? That if I want to find the exact value of that pink dot right there, what would I do? What is it equal to? Y naught plus h times the slope of that line, right?
Oh, yeah.
Yeah, the change in, right? Just rise over run, right? Simple as that, rise over run. So the change in distance between y naught and the pink dot is simply equal to the change in at h times the slope of the line, or the derivative, or in this case, that capital F of, right? Capital F, T naught, Y naught. So all this, there's nothing going on here, nothing complicated going on. All this is that I have my Y naught, the value where I start off, and I'm going to add the approximated change in vertical distance, which is simply the change in x times the derivative at that particular point in time. And I can always find the derivatives because the differential equation gives me the derivatives, right? That's what it does. This is basically an equation telling you all the derivatives that you want. You can ask it any derivatives you want and it'll give it to you. So this would give me the next one. Now let's say that, then what do you think I'm going to do next? I'm going to plug it in again, right? And I'm going to find some other slope. Let's say the slope of the tangent line this time looks like that. And if I use the same step size, then my solution will look, so T2, the same step size, right? My solution, I will approximate it to be right around there. And then, so you keep doing this, right? And then your solution would be approximately the, yeah, just connecting all the dots, right? And that's it. It's simple, right? Very, very simple idea. All you do, you find the derivative, move over, then find the derivative, move over, find the derivative, move over, find the derivative, move over, add them all up. That's it. So, so let's write this down. What we're doing basically is Euler's method tells us that the y of t sub I plus 1, so this is the next y value in our solution, is equal to the previous y value plus the step size times the value of the derivative at the previous y value. Does that make sense? I hope so. Okay, so we have a plan, right? So then how do we make use out of this? Do we do it by hand?
No.
No. What do we do? Yes, we do. We tell the computer to do it for us. So right now, what we're going to do, bam, we're going to bust out a program that'll calculate Euler's method, and after that, we'll plot the solution. Okay, so we're going to solve. Let's write down what we're going to do. We're going to solve the Am I too excited? We're going to solve the differential equation. dy over dt is equal to y plus t. Okay, wait. All right. So what does it mean when I put a percent? Comment. Okay, so that's what we're doing, right? That's what we're going to do. Now, the exact solution is, I wrote it down here before. So it's y of t is equal to 1/2 times e to the t minus 2 times t plus 1. Okay, this is my solution. Yes? Sound like a plan? All right. So, what do we need? What do we need to tell our program? Okay, so let's say we're going to go from 0 to where? 10. Sure. Why not? 0 to 10. Okay. And we already kind of saw the picture, right? So we have this picture. Oh, we had the picture. No. No dice here. Hold on. Oh, there it is. Okay. So we have our picture. So, well, why don't we go from, should we go from -10 to 10? Let's go from 0 to 10. Okay. So 0 to 10 sounds good. So we're kind of chopping it off right there. But that's okay. All right. What else do we need? The number of steps. Sure. Well, yeah, the step size is more important. So step size, let's do, so that's h, right? How about, let's start off with, how about we start off with 2? So if my step size is 2, then how many 5 steps, right? Okay. So let's do this. So t is going to go from A to B, and then in step size of h, so how do I do that? H in the middle. Okay. All right. We are rolling. Okay. So now,
Where did the exact solution come from?
Oh, I gave it to you.
Oh, okay.
Yeah.
Alright.
Yeah. You actually don't know how to solve those yet, but you will. Yeah.
Okay.
So for now, just accept that that's what it is.
Smell it.
Okay. So then, what else do we need here? Y. Well, okay. So let's go back to our our Euler's method here. So so this is what we're gonna do. We're gonna have to, of course, make a loop, right? Okay. So this loop is going to basically grab, so I need an initial y value. I need to know a starting point. So let's say you have a starting point. So we're going to start at y sub 0. And we're going to start at t equals to 0. So we're going to have a loop that takes that y value. It adds h times the derivative at the y value, which is simply plugging in the t value and the y value into the differential equation, right? Does that make sense? Okay, so let's put that in. This is no problem. So make a loop for k from 1 to how many?
5.
Okay, let's do n is equal to, let's make it n the length of t. What will that do? What is t? Yeah, t is the time, right? It's the t is the time values. So if I, let me do this just to make sure everybody's on the same page here. Oh, I need to save it, sorry. All right, Euler. Okay, run. Okay, so here if I look at t, so t is the time values that I step at, right? So n is simply the number of values that I have here. So when you put length of t, then that should give me, in this case, it should have given me 1, 2, 3, 4, 5, 6, right? So if I put n 6. So length just gives you the number of elements that you have inside of that vector. Okay, so all right, so I'm going to make a loop from 1 to n. Now notice I'm missing something. Before I do my loop, what do I need? I need to give my initial condition, right? So let's call that y of 1 because that's going to be the first y value. So this is my initial condition. So what did we say we were going to do? How about we go back to our picture and look for one that's going to give us something interesting. I don't know. About negative. Well, let's do 1. So 1 is, it'll look something like that. So not super interesting, but we'll change things around for fun later. All right, so that's my initial condition. All right, so then we said we are going to say that the next y value, so y of k plus 1, right, is equal to what? Y of k, right? So in the first loop, it'll be y of 1, which is the initial one, right? And I'm going to add h times the derivative. So now this is dependent on the actual differential equation. So in my case, the differential equation, I'll put it inside of parentheses, is y plus t, right? So it's going to be just y of k plus t of k. So notice that you're trying to see what's going on. You're calculating the next step based on what's happening at the present step. Yes? Okay. So I'll put a semicolon there and then end the loop. So this will make y, what's the size of y going to be in this case?
1.
After I run the loop? How many elements will y have?
However many n.
6, right? Okay, so 6, right? Because this goes from 1 to n is equal to 6. Now, can you guys see the mistake? There's a mistake there. So the last n, the n is equal to 6, right? So the last value here will be
Minus n plus
6, but here you're accessing the 7th, right? So then I need to change this. This should be from 1 to n minus 1, right? So it's going to go up until 5, which means that it's going to give me the 6th value, up to the 6th value. Otherwise, it'll go 1 over, right? Okay. Now that we have that, so this is going to give me, so these are my approximations, right? Yeah? Okay. So what I'm going to do is I'm going to plot the real solution. So I'm gonna do a new setup. So T real, let's call them T real, is equal to I'm gonna go from A to B, but I want my real solution to come out nice and smooth. So I'm going to do this in steps of 0.01. So these are different t values. And then I have my y real. This is going to be my actual solution. So I'm going to put in basically this, but making sure that I type it in properly. So this is going to be my real solution, which I gave to you, right? So I need to fix this a little bit. What am I missing here to make it? So here I just put it inside the comments, so it doesn't exactly matter how I write it. But when I put it down here, I have to fix some things. What are they? The dot on the power. Yep. What else?
Parentheses around the 1/2.
1/2. Oh. You don't need the parentheses there, but you do need times, right? Okay, so 1/2 times e raised to the t with a dot, and then minus 2 times t plus 1. Okay, and that should work, right? So notice that this is going to have a lot more values than my approximation, right? And that's so that I can get a nice smooth curve. So I'm going to plot that. So I'm going to plot t real, and then I'm going to plot y real. And let's see what that looks like, just for now. This t value is t real, not t. Duh. T real. Get real. There we go. All right, so let me change this to 0 to 2, 0 to 1. Okay, there we go.
Wouldn't it have just said that t was undefined? Wouldn't it give you that error?
What?
Huh.
All right, so this is the solution. From 0 to 2, my initial condition is at 1/2. Yes? Okay. So, all right, so this is my real solution. And so what I'm going to do is I'm going to plot the approximated solution on top of it. So I'm going to do, what you do is you do hold on right there, and then you want to plot, so it'll superimpose the next plot on top of the new one. So we'll plot t and y, and then let's do we'll do red stars. Okay, play. No.
I thought the initial condition was 1.
Oh, it is 1. Oh, that's why. This solution is with a initial condition of, that's why. Okay, negative 1/2. Thank you. Yes. We wanted, good job. Nice work. Okay. Good job. There you go. Okay. So, let's connect it with lines. So there's Euler's method. So this is our approximation. So see how, so I have this initial condition, we found the slope, boom. At that point you find the slope, boom. Find the slope, boom. And you can already see so this is the simplest method that there is, but you can already kind of see the problems, right? That if see how it's gradually getting farther and farther away as time goes on. And actually, let's make it longer. Let's make b 3. So let's go from 0 to 3, and then let's go from y equals to 2. Let's see what happens here. So you can see that, it starts off good in the beginning, but then over time it starts separating and separating and separating. So what's the only thing that I can do?
Increase the steps or decrease the step size?
Decrease the step size. So let's say we have it. And cut it in half, so 0.1. So we have twice as many points, right? So that's closer, right? But still, it's getting farther away, right? So I can get closer. And so that's a little better. But it can get expensive, right? So this is what's called a first order method, meaning that if you half the step size, then you decrease the error by about a half. So there are better methods available that you can, if you decrease the step size in half, you decrease the error by a fourth. That would be a second order, or an eighth, would be third order. So it's 2 to the, and so on and so forth. So what would that mean in terms of computational cost here? Yeah, you wouldn't need as many points, right? So like right here, if I make it h equal to 0.1, that error is pretty big. I mean, it's completely visible. So you would have to make it, let's get rid of the stars so that we can take a look a little bit better. But if I make it 0.01, right? So that's 100 valuations for every one, right? So that's, and even there's a visible error right there, and then of course you can make it even smaller, and so there's still a little bit, right? And you can of course calculate the actual error. The error, how do I find the error? Well, I would actually have to calculate it at the specific point, so I can't quite do that with the setup that I have, but but it can be done, right?
Would the error be the same for any point you picked on there?
No, it's different, right? Because you can see right away that
It gets bigger errors.
the error gets, oh my gosh, sorry. Uh-oh, I broke it. Program's broken. Hello?
Saw you do it.
What happened to my plot? Oh my gosh. What did I break? I don't even know what I broke. It was running just fine. It's not giving me an error. I crashed it. I totally crashed it. That's what you get with free software. No, it said ready. So anyways. So that's Euler's method. Now there's, okay. I guess I don't really need to do it again. So Euler's method, so we needed quite a few evaluations. So can you guys, any ideas on improving Euler's method? So how can I maybe improve on this idea here that I have? So here all I did is something very simple, right? I calculated the first derivative. So basically this is a linearization, right? So you find the slope of the tangent line. So, this is like back in Cap 1 what you did. You find the slope of the tangent line, approximate the function, right? This is basically what you're doing. Any ideas on how I can improve on this? Yes, and how would you write that? Hint, we've done it already. Yes. this is because remember, what do you remember the Taylor polynomials? The first degree Taylor polynomial is basically a linear approximation of your function, right? It's basically what we just did. So instead of doing a linear approximation, you can go one more, so increase the order, right? So you can think of this as, so you can use Taylor's methods. So you remember Taylor polynomial. So think of it as, so let's see. So y of, well, let's do this. So Euler's method you can think of as a first order Taylor's method, or Taylor polynomial of degree 1, because that's what it is, right? The linearization. So if you wanted to use a degree 2 Taylor polynomial, so this would look like, so if you wanted to take a step, what would the Taylor polynomial look like? So let's put a parentheses here. If you want to take a step from t sub I to t sub I plus 1. So it's exactly what we've done. It's just putting it in this framework. So it's really no different. Remember the Taylor polynomial, the first part is the value of the function, right? At the point where you're evaluating, which is, in this case, y of t sub I, right? So this is the first term of the Taylor polynomial. And then the second term, so the second term is exactly this one, right? H times f. So h times, let me see. I'll write it down. But it doesn't look like the Taylor polynomial expansion, but it actually is, because what does this capital F represent? Yeah, this is the function y. This capital F is the derivative, right? Because that's the differential equation. So this is the first derivative, right? And this h, do you remember seeing the h in the Taylor polynomials? No. But what does h represent? That's the difference between the values, right? Which is the x minus x naught in the Taylor polynomial. So that's exactly that term, right? So the first one was h to the 1. So then if you wanted to do, so it's degree 2, right? So you would have one more. So what would happen to the h? It would be h squared over 2 times the derivative. Yeah. So basically you're getting the derivative of this right here, this differential equation. Or you can think of it as the second derivative of y, right? And then if you wanted to get a better approximation, you would do another one, and then another one, and then, of course, as you add more and more terms, then the computational cost also increases. But this is definitely it would give you a better approximation than just the linear case. And then what would the error be? The error, remember so let's write this down so we don't forget. So we would have some stuff here. So that stuff, do you guys remember this stuff? So what would the next term be? By Taylor's theorem? You guys remember Taylor's theorem?
H to the n.
Yeah, so one more, right? H cubed at
F double prime.
F double prime at some point, right? We use psi, but I don't know.
What do you mean when you say the computational cost?
Well, that's a bad sigh, isn't it? Well, the computational cost, because if so for Euler's method, all I had to do is I had to evaluate the function at one point, right? So every step that you take, you evaluate the function once, and you add and you multiply. So that's your computational cost per step. Function evaluation, multiplication, and a sum. In the second order, the Taylor's method, you would have to do exactly the same thing, plus you would have to add an additional term where you square h and then you multiply that times the derivative of the function. So this is extra computational cost, but it gives you better accuracy. So that means that your step size, you can do it, make it bigger, so you wouldn't need to do as many evaluations. That's the idea. So you sacrifice in one way and you gain in some others. But so this right here, all this stuff this right here, this is the error term. So all that, so this is stuff. This is basically how far off you are. So you don't know exactly what that is, but it's some stuff there. So this is called a second order method, and so basically the reason why you can kind of see right here, this is the error right here, right? So let's put down the same thing for, it's kind of, this is really just kind of a brushing through here. Over 2. Okay, so in Euler's method, this is the error. Notice how, if you compare these two, notice how, so h typically, the step size is typically small, right? So imagine that the step size is 0.1, let's say, right? 0.1. So if you're looking at Euler's method, then you look at this error term, and so the error will be, somewhere in the neighborhood of 0.1 squared times some stuff, right? So 0.1 squared is 0.01, right? Yeah, okay. But now if you look at the same step size down here, your error will be along the lines of 0.1 cubed, which is 0.001. So that's how the error gets smaller. As you're kind of looking at this error term, and you go, okay, well, yeah. So because this is to the third, then the error goes down a lot faster. So this is a great time that if you're interested, later on in life, you can take a class in numerical analysis, and you learn all kinds of great things, and you see Taylor's theorem all over, and very fun times. Very what? Very what? Oh, no, I thought you guys said something.
He's agreeing.
Okay, one more idea. So this was idea number 1, Taylor's method. We said order 2, and we can do order 3, order 4, right? Any other ideas for improving this method? Not based on Taylor's? Maybe just thinking about sort of the geometry of our situation. Because the problem, if you go back to the picture that we weren't able to replicate because our program crashed, remember the problem is that our problem is that our slope becomes, where is it? There it is. Oh, okay. I'll run it in MATLAB, sure. Okay. Our problem is that our slope isn't as good as we would like it to be, right? So is there any way, any simple modification that you can think of that would maybe make your slope, I don't know, a little bit better? Yeah, so more steps, of course, but besides from more steps, so you want to take the same amount of steps. No, nothing comes to mind. Something simple like.
Oh no, I
Yeah, you should.
More steps.
No,
We already did that.
Yeah, we eliminated that from the possibilities. I mean, you can do that, of course, but that's not something simple, easy, not complicated. Something simple. Okay, I'll give you a hint. How about what is it?
Arc length?
No, simple. I said simple. Simple arc length. That's complicated. Let's say you wanted to approximate the so instead of doing from here to here, so let's say you wanted to kind of estimate the slope from there to there kind of thing. Maybe okay, I'll give you guys a hint. Is there a way you can use other points besides only the initial point to help you make your approximation?
Yeah, it could be any point anywhere, right?
Yes, that is correct. But if you wanted to, because right now what ends up happening is so if you look at your picture again, what ends up happening is you evaluate the slope at a point, right? And so you shoot off in that direction, and then you'll overshoot, right? So you overshoot, and then so the next one, you're already off, so you overshoot again, and so then you overshoot again, and so is there a way to sort of eliminate that kind of an error?
Do a first degree at a different point. And that would be exactly right on it.
Yeah, but that's complicated. Something simple, something just simple that you can do. An easy modification.
Change your initial point.
Yeah. No. Okay. All right. Well, I'll just tell you that it is getting kind of late, so I'll ruin the fun. Okay. So here's an idea. This is just one idea. I mean, it's not the idea or anything. So you have a point here, right? And you find the slope. And you approximate the slope at this point, and let's say it looks like that. So instead of using this slope only to get to the next point, so what you do is you calculate the slope at the first point, calculate the slope at the next point, and then you use the average of the two as the two slopes, right? Because it's really probably something not there, but probably somewhere in between, right?
Oh.
So, what is it? That wasn't simple?
No, I said it.
That what? Oh, you said that. You did, but you didn't. Yeah. See, I told you guys. You guys should. So this is called, if you want to look it up for fun. All these, by the way, aren't really in your book. These are just fun things that I thought you would like to know. So these aren't in your book, but if you want to look it up, this is called Hume's method, and it's basically what we just said. So this is Wikipedia probably has some good info there, but you take the y value, and then you add the average of the slope at t sub I, y sub I, and the slope at t sub I plus 1, y sub I plus 1. And then find the average. So this is a simple sort of, it's also called a predictor corrector method, because it's like you predict where it's going to be, and then based on the slope at that point, then you correct it a bit to make it more in line with what it's going to be. Another neat thing to look up on Wikipedia. Predictor corrector. Predictor corrector. Pi plus 1 and yi plus 1. So basically the average of the slope at that point and the next point. Thumbs up? Okay.